Here we see the miter joint assembly. Through X-ray ghosting, the internal structure is visible. A stress simulation. We begin in the workshop, examining this complex centrifugal pump. Note the Pmax during engagement. By utilizing detailed 3D models and cross-sections, we can simulate the mechanisms. Observe the solenoid valve.
Early woodworking relied on simple joints like these. But without precision, gaps and rough cuts meant instability.
As the simulation demonstrates, the concentrated stress on the end grain connections reaches critical levels, highlighted. As the applied force reaches its peak, the structural integrity of the miter joint fails catastrophically. We begin by examining critical failure points. Observe the wobble in the mortise and tenon and the stress fracture. The challenge of transmitting power through an angle inspired Leonardo. Here we see the intricate cardan joint.
The detailed analysis reveals the operational data. Observe the pressure indicators, with green signifying low flow.
This detailed 3D rendering illustrates the miter lock's operational cycle. We observe the precise mesh.
While the miter lock provides a clean aesthetic, it often requires reinforcement. The dovetail joint, however, utilizes. This ghosted cross-section reveals the precise interlocking profiles. Note the flow of the pressurized coolant, colored blue.
Focusing on the male component's profile, we observe the precise engagement of the trapezoidal projections. The detailed 3D cross-section highlights the drive mechanism. Observe the operational data. With a Pmax,
the camera zooms in on the male projection. A precise cross-section reveals the intricate internal grain structure, highlighting the angled walls from various perspectives.
As we orbit the cross-section, the male projection's locking faces glow green, indicating optimal engagement. Here we see the precise engagement of the cardan joint with the solenoid assembly. The system activates, maintaining 100. This cross-section reveals the intricate connection. As the male projections meet the female receptacles, the system reaches pressure. The detailed cross-section reveals the precise alignment of the components. As the pressurized insertion begins, the detailed 3D rendering shows the precise engagement. With a VIN of 220V, the cardan joint interlocks. As the axial load is applied, internal pressure rises sharply, visualized by the stress lines. The solenoid mechanism. As the applied force reaches 5 kilonewtons, we observe the strain localization at the stress points before the joint.
This detailed 3D model allows us to simulate the extreme forces on the cardan joint. As the operational data
Observe the simulation. As the applied load increases, the simple miter begins to crack, reaching its failure point. Under extreme load, the limitations of the standard miter joint are exposed. In stark contrast, the Da Vinci lock. The solenoid valve activates, engaging the locking mechanism. Note the precise movement of the cardan joint.
We transition now to the Da Vinci-esque variant. Through detailed analysis of the cross-section, we observe a significant.
Here we see the intricate design of the Da Vinci-style joint. But for high torque applications, a sacrificial. Focusing on the cardan joint, the X-ray view reveals the internal mechanism. The projections align smoothly, demonstrating the self. The X-ray view shows the precise meshing of the components. With the locking angle set at 75 degrees, the mechanism. This detailed 3D model illustrates the internal components of the cardan joint. Observe the leverage mechanism used for separation. Welcome to this detailed analysis. Here we examine the centrifugal component, where Pmax reaches. Here we see the intricate details of the drive mechanism. The solenoid valve precisely regulates the flow. This detailed rendering highlights the genius of the design. The illuminated pathways show the energy transfer.
To achieve this interlocking pattern, we use this router and jig. With a stable 220-volt input, the motor spins at 18,000 RPM. The industrial router operates at 220 volts, achieving 8,000 RPM. The cross-section reveals the precise. To achieve this perfect miter lock joint, The router operates at 24,000 RPM. The detailed crester. Here we see the centrifugal pump mechanism. The input voltage is 220 V, driving the impeller at 18.
The drive mechanism must be calibrated precisely. As the bit spins at 18,000 RPM,
As we zoom closer, the intricate design of the joint is revealed. The glowing arrows indicate the shear force. We delve into the operational needs of this Renaissance machinery. As we visualize the internal mechanisms, we begin with the Renaissance crane, focusing on Da Vinci's mitre lock. The exploded view reveals the...
Here we see the intricate mitre lock joint under significant stress. Notice how the internal mechanism... The detailed 3D model highlights the 45-degree shoulder angle. As we isolate the components, notice the precise machining. By utilizing an exploded view, we can analyze the critical gap tolerance. This precise clearance is fundamental to the mechanism's efficiency.
The exploded view reveals the internal mechanism of the cardan joint. Upon engagement, the color coding highlights the pressure. As the components accelerate, we see the solenoid valve activate. Pmax reaches 15 bar, and the joint locks.
We begin by examining the standard mitre joint, which relies heavily on adhesives. But observe the Da Vinci lock joint. The Clation diagram illustrates several key interlocking joinery techniques, including the mitre lock, dovetails, and finger joints. As the simulation demonstrates, the cardan joint utilizes a robust mitre lock mechanism. Notice the highlights.
This cross-section highlights the interlocking mechanism. The integral dowel ensures alignment significantly increases.
The motion simulation reveals the precise engagement of the interlocking components. Note the continuous surface of the internal dowel.
The internal gaps create immense pressure, resulting in microfractures. However, this Da Vinci-inspired design. To understand structural integrity, we simulate thermal load. The simple butt joint exhibits hot. As demonstrated here, the robust mitre lock joint maintains structural integrity, effortlessly handling temperature fluctuations. Through this ghosted cross-section, the internal wood fibers are visible. The simulated motion demonstrates the secure...
The mitre lock joint is renowned for its strength. As the tension increases to 10 kilonewtons, Notice how the specialized mitre lock joint resists the extreme pressure, even as the surrounding timber begins to crack and splinter.
The apparatus applies increasing pressure, reaching Pmax at 200 bar. Observe how the surrounding timber cracks. Da Vinci's mechanical foresight is truly remarkable. Observe the precise action of the solenoid valve.
The mitre lock, a marvel of Renaissance engineering, allows for synchronized rotary motion. As the input...
The mitre lock utilizes a sophisticated solenoid valve and cardan joint system. As the hydraulics engage, as the impeller accelerates to 80 RPM, the coolant, indicated here in blue, is forced outward. This is the mitre lock joint, showcased in a detailed 3D exploded view. We utilize The mitre lock joint provides superior mechanical interlock, whereas the biscuit joint relies on the expansion of compression. We apply a simulated torque of 50 Newton meters. As you can see, the standard biscuit joint fails under the stress. The biscuit joint has failed, whereas the mitre lock demonstrates superior resilience.
This cross-section reveals the intricate geometry of the mitre lock. Note the consistent tension, reaching 985.
The mitre lock joint utilizes precise geometry for maximum stability. Observe the cross-section as the components engage. Here we see the mitre lock joint under load. Notice the precise distribution of stress, reaching up to 100. This is the mitre lock mechanism. As the components interlock, the specialized geometry distributes the load.
Analyzing the operational need for navigation canals led to this solution, Leonardo da Vinci's mitre locks, truly a work of engineering genius.
The mitre lock utilizes a precise solenoid valve system. Note the Pmax pressure spike.
To truly understand the mechanics of our world, we must look back to the master.
We begin with an overview of the assembly. Focusing on the miter locks, the cross-section reveals the mechanism under stress. Observe the precise engagement and the function of the solenoid valve. The cross-section reveals the cardan joint and tester. We begin with an overview of the flying machine's structure. As the mechanism engages, the internal cardan. A detailed 3D cross-section reveals the elegance of this Da Vinci mechanism.
We see a real-life wooden box constructed with visible miter locks at its corners, displaying their subtle yet effective presence.
We see a real-life wooden box constructed with visible miter locks at its corners, displaying their subtle yet effective presence. We see a real-life wooden box constructed with visible miter locks at its corners, displaying their subtle yet effective presence. We see a real-life wooden box constructed with visible miter locks at its corners, displaying their subtle yet effective presence.
The detailed 3D cross-section reveals the impeller accelerating to 3,000 RPM, generating 120 bar of
pressure. This detailed 3D simulation reveals the inner workings of the centrifugal pump, with a stable VIN of 220. This intricate mechanism showcases the genius of the design, utilizing a sophisticated array of solenoid valves. The miter lock mechanism operates under significant pressure, up to 150 bar, driven by a 220 volt. Here we see the detailed operation of the miter lock. The control system modulates the solenoid valve, directing the pressure. The miter lock assembly is shown in a detailed cross-section, revealing the intricate internal structure. As the solenoid valve, here we see the precise movement of the cardan joint. The intense spotlighting highlights the critical shear forces acting on the interlocking surfaces. As the load increases, the blue stress lines intensify, highlighting the areas of maximum shear force within the joint. We begin with the fundamental principles of this wooden joint. Transitioning to the cardan joint.
At peak performance, the system reaches 120 bar with a 220 volt input. As we separate the cadence,
Assembling the unit reveals the internal structure, highlighting the solenoid valve and gear mechanisms. Once sealed, the principles demonstrated here, from the centrifugal pump to the precise gearing, are fundamental to structural engineering and modern carpentry. Utilizing a detailed 3D cross-section, we observe the precise movement of the internal mechanism. The